Welcome back, everybody. We'll just continue now with Maria's talk, including the last in her series.
Hey, so I want to pick up from where I left off last time. So last time we talked about generalized flag varieties as just some arbitrary linear algebraic group, G, and a Brill subgroup. And then G mod B was a generalized flag variety. So we had GLN mod B in the classical case. And there's a couple things that I didn't end up saying that I realized I should have said, because there were a couple questions I got afterwards pertaining to this. So first of all, I didn't say that all Borels are conjugate to each other in any of these groups. So any two Borels are conjugate. So that's why when we had that Lee-Culkin theorem that said, any solvable subgroup consists of upper triangular matrices in some basis, you can always take the Brill, containing that, and that's going to be upper triangular in some basis, by conjugation. And there's actually another way of thinking about the flag variety, which I think is just worth mentioning because it comes up sometimes, which is you can actually. So here's another little exercise that then you can show the normalizer of a Borel, or at least for the GLN case, it's not so hard to show that the normalizer of B is B in G. So meaning GB G inverse is equal to B if and only if G is in B. And what this means is that sort of the subgroups conjugate to a given Borel, meaning all the other Borels, are in correspondence with the cosets in G mod B. So there's a one-to-one correspondence that looks like this. So you can, GB is also equal to B if only if G is in B. So we can alternatively think of the flag variety as the set, which is sometimes called fancy B, of all Borels, set of Borel subgroups. So that's just another thing that comes up sometimes when you're looking at flag varieties. And then it was also asked, when is there a Schubert decomposition story and everything for these? In fact, just about always. So, for instance, if G is a semi-simple algebraic group with Weil group W, then there's something called the Bruhat decomposition of G, which is related to Schubert decompositions. So the Bruhat decomposition says that G can be written as, it breaks up into sets that look like this. BWB for W in the Weil group. For instance, in GLN, this is saying any matrix can be written uniquely as a permutation matrix multiplied on the left by an upper triangular and on the right by an upper triangular, which is kind of an interesting factorization. And then this actually descends to the Schubert decomposition of the flag variety. You just take sort of, the Schubert cell XW is going to be one of these, the image in the quotient, right? Something like that. So, so it's pretty general. The stuff that, all the Schubert decomposition stuff does generalize to flag varieties. And then there's some subgroup of the Weil group that you might use for a partial flag variety that indexes those Schubert cells. And yeah, so we talked about partial flag varieties. But as far as like a Littlewood-Richardson rule goes, there's only a few cases in which we really know the combinatorics. So remember we had G mod P, for P a parabolic subgroup between B and G. And a maximal parabolic gives us a Grassmannian. So we talked about that, and then this today I want to go into a very specific Grassmannian that's not the ordinary Grassmannian, which is the orthogonal Grassmannian. And there's a lot of nice combinatorics there, and a little bit of Richardson rule, and everything you might hope for. So let's start on the next variation on the theme of Schubert calculus, and that is so we're going to define. So we defined last time the orthogonal Grassmannian of k-planes in, and I'm doing the autoorthogonal Grassmannian here, k-planes in 2n plus 1 dimensional space that are isotropic. I'm going to take the sort of maximal one where you take n planes. And so this was some quotient of SO2n plus 1 by a maximal parabolic. And we thought of it as, so we think of this as the set of isotropic n-dimensional subspaces V of C to the 2n plus 1. So isotropic meant with respect to some fixed symmetric bilinear form, right? So last time I just took the usual dot product just as an example, but for today I want to fix our symmetric bilinear form to be something else because it makes the combinatorics work out nicer. So I want to take the form that takes two vectors and so say A1 through A2n plus 1 and B. And takes basically their reverse dot product. So you take A1 with B2n plus 1 and A2 with B2n and so on. So AI, B, 2n plus 2 minus I. So you'll see in a minute why this is a nice form. But then remember, isotropic means that the inner product of V with W is 0 for any V and W and V. Okay. Actually, I should say the reverse dot product it appears in the literature in different forms with different coefficients, like attached to these, which make it nicer in some cases, but I'm just using the simpler version here. Okay, so one reason this reverse dot product is nice is that the standard flag has a nice condition now. So remember, this is, you just take the basis vectors and generate a flag. This is orthogonal with respect to this form, meaning if you take all the things in f sub I and you take all the things orthogonal to something in f sub I, that's exactly the space f sub 2n plus 1 minus I. So the complementary flag parts are orthogonal to each other. That's what we mean by an orthogonal flag. And orthogonal flags are going to be the flags that we define our Schubert varieties with respect to in the orthogonal Grassmannian. You don't just take any flag, you take the orthogonal flags. So that's one reason we could have picked any symmetric bilinear form and still worked with orthogonal flags with respect to that, but now the standard flag is one we can work with. Yeah?
This looks as if we are multiplying by the longest element of S at 2n plus 1. Is it meaningful to look at it this way?
You mean because we're reversing this?
Yeah.
I don't know. I mean, S sub 2n plus 1 isn't the Weil group. It would be like semi-direct product sum Z2 to the n. Maybe it comes in somewhere. I'm not
I was
sure.
thinking because Bn is like a folding of A sub 2n, something like that.
I'm not sure. If anybody else has an insight, feel free to speak up. I don't know. I just think of it as convenient because of this. Anyone would give you the same combinatorics. It's just one that's convenient to work with. So there's there's a natural embedding then of the to understand the orthogonal Grassmannian. Of course, we're just taking isotropic subspaces, so we can embed this in the ordinary Grassmannian. And then to understand the Schubert decomposition, what I want to say is, if we have a V in here, it's in the Grassmannian, so it's in some unique Schubert cell with respect to the standard flag, say. So let's say it's in omega lambda. I claim that lambda has to be a very specific thing for this to be isotropic. So my claim is that lambda has a certain symmetry. So it's symmetric about the staircase. I'll define this in a second. Okay, so in GR 2n plus 1n, what's the important box? It's the n by, or k, it's usually k by n minus k. Here k is n and n is 2n plus 1. So we actually get an n by n plus 1 rectangle, and that all our partitions live in. I want to make it 4 by 5. Let's try to do this. Okay, so there's 4 by 5. And then I want to take a different color and split this into 2 equal pieces by drawing a staircase like this. Can you guys see that color against the white? Okay, okay. So I'm going to divide it into an upper triangle and a lower triangle, and then I want to take partitions that are symmetric about sort of, shifting this triangle up by 1 and reflecting, I guess. Here's an example. If I take 3, 1 here, I basically want to take conjugate 3, 1 here. So in other words, well, this would give me the total partition being 4, 3, 1, but its shape is symmetric about the blue. So lambda 4, 3, 1. Actually, I should not call this lambda. I should call it something else. I'll switch my notation later. But yeah, so this is symmetric in this diagram. And I mentioned last time that I'm going to be focusing on this n case, not k-planes. And one reason is there's not this nice symmetry when you have other dimensional things. So this is why the combinatorics is pretty specific to this case. Okay, so why is this true? Why does, for isotropic subspace, we have to have a symmetric partition? Well, let's look at, for instance, for this particular partition, what does omega lambda look like? This is the Schubert cell that, in our standard notation, is formed by, we take our staircase and we add 4 to find our first one, and then we add 3 boxes to find the next one, and then the next one is here, and the final one is in the 0th place. And so there's our pivots, and then we have our ambiguous entries that can be any complex numbers. We have one extra row here. And as a sanity check, this should be 9 by 4. 2, 3, 4, 5, 6, 7, 8. Yeah, okay. And then there's 0 everywhere else. Okay, and then if you notice from, for this particular partition, if we label our columns, the positions of the ones have a very nice property. They have the property that if one is in position I, if one of the pivots, one of these is in position I, so column I, there is no one in column 2n plus 2 minus I, so the complement one. So, for instance, there's a 1 in position 3, there shouldn't be 1 in 7, right? There's 5. The middle column doesn't have a pivot. It's sort of opposite symmetric, and this holds. So here's an exercise, which I have actually as an exercise in the lecture notes. This is equivalent to this property is equivalent to lambda being symmetric. So you could just check the combinatorics there. but then the point is, if it doesn't have that property, right? If there was a 1 in the 7th position instead, we could have taken the this row, the inner product with this row, and this 1 would be paired with that 1, and nothing else would be paired. Everything else would be 0. So you would get a non-zero inner product, and so that would mean it's not isotropic. So that would mean, so if lambda is not symmetric, then any V in that Schubert cell is not isotropic. And that finishes the proof. So that's why symmetric partitions are going to be what's coming up here. And for that reason, we're actually going to sort of cut everything in half and just consider what's called a shifted partition, which is the upper half of this picture. Maybe before I do that, I want to check also that all of these symmetric partitions appear and construct the Schubert varieties in the orthogonal Grassmannian then, which will be the intersections with this. Yeah, which is what I'm going to say now. Yeah, exactly. So we're going to, right, the Schubert varieties are going to be basically the omega lambda for symmetrics intersected with the orthogonal Grassmannian. Yeah. So yeah, to get towards that, I'm trying to sort of build it up intuitively before I just state the final thing, but he jumped the gun.
How OG are you?
What? Okay, I must be like at the board and not able to think that I didn't get the joke, but oh well, I'll have to kill it. All right. Yeah, so we can ask, so which elements of this Schubert variety now are isotropic? Because we know if it's isotropic, it has to be in a cell like this, but now not all of these are going to be isotropic because we might have these stars multiplying by a 1 somehow to get a non-zero inner product. So suppose V in this is isotropic. So I'm going to claim that basically, if I label, let's label the entries of V now. Actually, replace these stars with letters. Let's do B, C, A, B, C, D, E on the bottom row, and then F, G, H, I, J, K, L. Oh, and I have this extra 1, it shouldn't be there. So I claim that if I put these numbers into my important box where they fit, I'm going to get some relations on them that say that the values of A, B, C, D, F, and G, the ones on the lower half, uniquely determine the ones on the upper half. And so the dimension will be exactly half the dimension for the Schubert cell in the orthogonal Grassmannian. Let's see how this works. So I'm going to label my rows like this, just to refer to them as something. This will be vector 1, 2, 3, and 4. If I take the fact that, so let me draw a little bit where the dividing line is, just roughly. Here's the upper half and lower half I'm trying to eliminate. So if I take the inner product of 4 with 1 first, this is going to eliminate L, basically. So this is 0. That means 1 times L plus A times 1 is 0. Everything else, all these other terms are 0. So we get A plus L is 0. And so L is just minus A. So if whatever I pick for A, that determines L. Okay. Then I can sort of eliminate the rest of the variables by going from the top and traveling left like this. So next I'm going to eliminate K, and then J, and then I, and then H, E by showing that each of those can be written in terms of things to the lower left of them. So let's look at K. Well, K, and this all boils down to this property that the ones are in sort of reflectedly opposite columns. So if you want to if you want to eliminate something that's in a starred position, you find whatever row has a 1 that's in the opposite position. And then you take that inner product. So if we want to eliminate K, we also multiply it by row 4. So because it's isotropic, 4 and 2 is 0. This gives us k plus, now we have to be careful about what else pairs, 0 with j, b with 1. K plus b is 0. Okay, so k is eliminated in terms of b. Then we can eliminate j by taking actually 3 with 2. So I'll just write 3 and 2 give whatever it is. J is minus f, I guess. These are pretty simple. And then if we want to eliminate I, we do 3 and 4. So this is a little more complicated. You'll get more terms here, but it's still fine. It's just all things to the lower left. I plus A goes away. I don't remember what this is. 0, 0. I think we get GC and D. Okay. Okay. So I is minus GC minus D. And then H is going to be eliminated by, now this one's interesting. So this is multiplying 3 with itself. So so now you actually get 2 copies of H, because when we're going this way, we're multiplying 0, 0, and then H with 1, 0, G squared, another H with 1. But we just get 2H plus G squared is 0, which is fine. So H is G squared over 2. So maybe this doesn't work over characteristic 2 or something. I'm not sure. But it definitely works over C. And then finally,
Is it 2G plus H instead of 2 plus
I think it's 2H.
Can you do the, so you're pairing 0 with I, and then
0 with I,
and 0 with H.
and 0 with I, and then 0 with 0,
Oh,
and then
I
1
see 0.
with H. Sorry. Let me write the zeros, because this is, yeah, sorry. I should have written the zeros to actually see what's going on. It's just that now they look like O's. But,
That's okay.
okay. Yeah. Anyway, and then 1 with H. I mean, it has to be 1 with H twice. I mean, that's how we're pairing it as the same row. And similarly, when I eliminate E with row 4, it's going to also give us a 2E. Plus C squared is 0. And everything else you can check is 0. So you get other terms, but the point is we're going to gradually eliminate down this way. And then to show it stops, like the elimination sort of stops here, it's a combinatorial argument. I have the full argument written out in the lecture notes if you're curious. But there's, it's also something you can try on your own for fun. This is just the idea of how it works. Okay. So, right, so that means that we really can ignore 1/2 of this picture. And the way I did it, I mean, these are kind of the free variables, and so we should be ignoring the upper half, but usually people draw shifted partitions in the upper half and ignore the lower half. So that's what I'm going to do. So we're going to define a shifted partition. To be basically the upper half of this, but we're just going to define it as a strict partition. So a strictly decreasing sequence of positive integers. So we'll write lambda is, again, lambda 1 through lambda k, and now we have greater than or equal to signs. Some r. And we draw its shifted Young diagram. To be just the Young diagram where the ith part is shifted over I times. So shift I row I steps to the right. Okay, so for instance, here's the Young diagram of 3, 1. So I shifted over, I kind of shifted this over by 1, and then I shifted this over by 2. So it's just the upper half up there. So here's lambda is 3, 1. And then, so I said I was using sloppy notation. I'm going to call the symmetric one lambda bar, actually, from now on. So I'm going to define, this is probably too low. What should I erase, actually? Yeah, okay. Yeah, so for a shifted partition, lambda, I define lambda bar to be its doubling to give an ordinary partition. So just sort of take the reflection in the staircase. So here, if lambda is 3, 1, then lambda bar is 4, 3, 1 from that picture. And then, right, and so then we had the important box is n times by n plus 1. Now all our shifted partitions are going to fit inside a certain triangle. So let's call it the important triangle. Is the just sort of n by n upper triangle, which I might just write as a triangle like this. So we're going to erase the lower half from this diagram now. Okay, so now we can finally just define the Schubert cells and Schubert decomposition explicitly for the orthogonal Grassmannian. We're going to just say basically what Stephen said before. So we can define the Schubert cell and I'll write X again, even though it's the notation I used for the flag variety, but it's what I've seen used for this. Let's use X lambda open of a flag, and again you can define it now with respect to any flag to be, you can define it as the intersection of omega lambda hat with the orthogonal Grassmannian. Explicitly, we can say, in terms of coordinates, just translate what we had for the Grassmannian using the doubled partition. So this is going to be the dimension of V intersect the rth part of the flag is I whenever R and I satisfy these inequalities, n minus k plus, oh sorry, not n minus k, this should be, whoa, I wrote that wrong. Yeah, that should, n minus k is n plus 1 in this case, yeah. N plus 1 plus I minus lambda bar sub I, the ith part of the doubling, is less than R, is less than or equal to n minus k, or sorry, n plus 1 plus I minus lambda I plus 1 bar. And then similarly, the Schubert variety is the closure of this, which is exactly the same formula as for Grassmannian, but you double the partition. So set of V and OG such that dimension of V intersect F n plus 1 plus I minus lambda I bar is at least I. So if you want to compute explicitly with subscripts, as sometimes is necessary, there they are. But yeah, the easier way of saying this, of course, is that this is just the intersection, even for any flag, this is the intersection of omega lambda, the whole Grassmannian one, with the orthogonal Grassmannian. Yes, I did. Thanks. Thanks.
But I guess, I suppose it's true that this is one D orbit where D is super element of D.
What is the cell?
The question before was whether there was a unique Schubert cell for OG, right? To make a lambda surf.
This?
Yeah. So I mean, the definition of Schubert cells, right, for OG is that they're the B orbits on G mod P.
B orbits on G mod P.
And
Yeah.
on OG, I guess.
Sure.
So is this it? I mean, so the question is just whether this is actually B orbit. But where B is the zero for the reflection.
Well, you mean whether this would be the
Right.
B orbit?
Yeah.
I mean, I guess it has to be.
Is it an atom space of the right dimension?
Well, yeah. So right. So we can easily say what the dimension is. I mean, the dimension is. We saw that it was determined by the.
Right.
Just anything for here, and then these are determined. So yeah, it's C to the number of lower squares.
So I guess it probably follows from that.
Yeah. Yeah. So yeah, let's break down the dimension. So dimension of for a shifted partition, the dimension of the Schubert cell is. Well, I could just say this is isomorphic to, of course, it's affine, right? It's C to the n, whatever the size of the triangle is, n choose 2, I guess, minus size of lambda, right? Oh yeah, I didn't say. I mean, for shifted partitions, we also just say the size of lambda is the subset size of the first, right? We don't double it or anything. Yeah, and then the dimension of this enclosure as well. Is the same thing. So it's a. Do I need n plus 1 choose 2? N plus n. Yeah. N plus 1 choose 2. Right. Yeah. So it's affine. And actually, it's kind of interesting. So in the ordinary Grassmannian, we have this closure being a union of Schubert cells itself. We saw this CW complex, right? And this, so this is, we know it's the disjoint union of the Schubert cells for omega mu. So this closed one is the open cells for mu containing lambda strictly. And now here we actually have to, even though we're intersecting, we have to symmetrically contain things, but then as shifted partitions, it's still just containment, right? So here no, I can't symmetry. I need different notation. So I'll write a shifted partition as, I'll make it rho this time to distinguish it from what I did rho. So this is x tau, where again, tau is a shifted partition whose diagram contains this. But if I was going to see what is that in the Von Grassmannian, like if I added this box to extend this partition, I'd also have to add this box symmetrically down there to get the right intersection. So, just interesting. Yeah, so now that we have the Schubert cells and Schubert varieties, just like we did last time in both the Grassmannian and the flag variety, we want to know how do we intersect them, meaning what is the cohomology rate of the flag and Grassmannian. So now we want to compute the cohomology ring H star. So we know this has to be some ring whose generators are that has a basis indexed by shifted partitions or partitions into distinct parts. And it turns out the right answer is what's called the Schur P functions. These are a type of symmetric function, but they live in a subspace of the symmetric function. So this is going to be a certain quotient of, take the symmetric functions generated by odd degree power sums. So just take P1, P3, P5, and so on like that. And then we're going to quotient by certain things that don't live inside of the important triangle that I'll fill in this later. But essentially, it's the symmetric functions with odd degree power sums. And you can see, I mean, sort of odd degree there's this theorem, odd degree partitions into odd parts correspond with partitions into distinct parts. There's lots of different proofs of this fact. So at least dimension-wise, this is sort of the right ring. And then there's something you can do. You can make, so in order to define, so we're going to define these sure P functions, capital P lambda, and that's going to correspond to the homology class of one of our Schubert varieties. And to define P lambda, these are, so I'll write sure P. These are defined pretty similarly to the sure functions, but for shifted tableau. So what's a shifted tableau? So a shifted semi-standard Young tableau is a way of filling, let me just draw one and then I'll define it. Let's see, I want to draw a skew shape. Actually, I'm going to define P for skew shapes, and I can take skew shapes in the shifted case just like we do for the ordinary. We just cut out a skew partition, or we just cut out a shifted partition from another. So let's draw. Okay. So I'm going to cut out this inner shape, and then my shifted partition is going to be, let's say lambda is six, 4, 2, 1, and mu is 3, 2. So this is the shape, the not shaded stuff is lambda over mu. And then I'm going to fill the boxes with letters from an extended alphabet. So now we can have 1' entries as well as 1s, as well as 2' as well as 2s, and so on. And they're ordered so that the primed entries are always thought of as smaller than the unprimed. And they have another rule, which is that, so semi-standard usually means it's weakly increasing across rows, strictly increasing down columns. Well, that's true for the not primed entries. But then we have primed entries too, and those actually have the opposite rule. So I'm allowed to put 2 1' in the same column, but not in the same row. And then, let's see, I have an example here where I have other things going on. But I can put 2 1s in the same row, but not in the same column. Okay. Yeah, so basically, we still have entries are weakly increasing across rows and down columns. And then repeats can be, so primed entries can repeat in columns and unprimed in rows. But not the other way around. Not in columns. Not in rows. Okay, so it's a little more complicated when we get to the shifted case. And if I have time, I'll define shifted jeu de Decan and how this comes from actually doubling and considering the general picture. It's actually pretty natural. But so what can we do with these then? So there's a couple different variants that people think about. The interesting thing about these shifted partitions is that the sort of standardization order that you want to think of it is different from the reading order. So we can still define the reading word, which comes in handy. You know, the reading word is reading how we usually read tableau, which in this case you read the bottom row first and then the next row and so on. So 3, 1, 1, 1', 2, 1', 1, 2'. Is that what I have? Okay. So that's the usual reading word. But then, and I want to define the content, or the weight, to be the sequence where usually we count the number of 1s, count the number of 2s, and so on. Here I'm going to lump all the 1s and 1' together, and all the 2s and 2' together, and so on. So there's 5 1 and 1' total, and there's 2 and 2' total, and 1, 3. And then so in ordinary semi-standard Young tableau, the standardization order comes from the reading order, meaning how do we break ties if we need to break ties. And here we want to actually think of the standardization ordering being opposite for the primed and unprimed. So the standardization says we're going to read, the standardization order is read the 1 primes first from in reverse reading order. Then the ones in reading order. And then the 2 primes in reverse order and the 2s in reading order and so on. So I would actually, so this tableau, if I was going to standardize it into a standard tableau, I would write it as, I'd take the 1 primes going sort of down and left, and then the 1s going up and right. I'd label this 3, 4, 5. And next I count the 2 primes and the 2s and the 3s. And so I get a standard tableau that looks like this. It sort of respects the ordering. And I mean, this is important because, I have to order this 1 prime before this one in order to get a standard tableau, right? But what's interesting is then this 1 here, it doesn't matter whether I call it a 1 or a 1 prime when it comes to just thinking of the standardization order. So if I change this to a 1 prime, I would still label this 1, 2, and then 3, right? It doesn't matter at all. So there's different conventions with these shifted tableau as to whether the diagonal entries can be primed or not, and whether the first 1 or 1 prime can be primed or not. So we're going to see all of these different variations. So in particular, I want to define the set of shifted semi-standard tableau sub Q. I'm going to call these Q type of a skew shape lambda mu to be the set of all shifted tableau of shape lambda over mu. And I want to have no restriction on the priming at all. But then I also want to define shifted semi-standard tableau sub P to be the set of shifted tableau of this shape such that the diagonal entries, the ones that actually sit aside that staircase, are unprimed. Okay, so these are a strict subset of those. And then I'm going to define 2 separate types of symmetric functions. So we defined the shear functions before to be the set of, is the sum of x to the t over t semi-standard Young tableau, or let's say anything like that, right, in the classical case. And now we're going to define the shear p and shear q functions according to these sets. So p lambda, well, let me start with q because it's the easier one. Q lambda mu is the sum of x to the, now x to the t means x to the content in this sense. We lump the 1s and 1 primes together. So we're still in the algebra of, we still have just x1, x2, x3 as our variables. So here's t in SHST sub q of lambda over mu, and p is the same thing for p. So I guess I could put x to the content here. Maybe that makes it more clear. Okay. So yeah, I mean, as an example, the monomial I would assign to this guy is x1 to the 5th, x2 squared, x3. And then I get the monomial that I add here. So these turn out to be symmetric functions. They turn out to be in the ring generated by odd degree power sums. they're also dual to each other. So if I take just the straight shape ones form a dual basis. P lambda Q mu is delta lambda mu. So they're like all those other dual bases we've seen. And then and they also, for those of you who know about McDonald polynomials and Hall-Littlewood polynomials, they're specializations of these, actually. So if you take the Hall-Littlewood polynomial, there's all different ways of writing Hall-Littlewood polynomials. One of them is P lambda of xq. It's a symmetric function with an extra parameter q, and if we plug in -1 for q, then if lambda doesn't have distinct parts, it's going to vanish, and if it does, then it's going to be P lambda, and same with Q. So that's just sort of an aside. I'm not going to define Hall-Littlewoods, but okay. So these actually, one reason I decided to talk about the orthogonal Grassmannian as a variant of the whole Schubert calculus world is that the combinatorics that comes up, these Schur P and Q functions, they come up in lots of different contexts. In fact, I think the first sort of other context they came up in was studying projective representations of the symmetric group, which are so like a usual representation is a morphism to or a map to GLN. These are going to be maps to PGLN, and then classifying those irreducible representations. So. Okay, so those are the Schur P and Q functions, and then I claimed that this is the homomorphism. I'm not going to prove everything in detail here, all our Pierre rules and duality rules and everything to build it up, but we can now talk about what is the Littlewood-Richardson rule on this side. That tells us how to intersect our Schubert varieties on this side. So here's the Littlewood-Richardson rule. Well, it's a rule for multiplying Schur P functions and expressing them back in a P Schur basis. So I'm going to call the coefficients F nu lambda mu. I've seen that in papers. And before I talk about the combinatorics, it's kind of interesting how, the Schur functions are self-dual, but for P we need Q as its dual, and it's just off by a little bit. I mean, the partitions or the tableau that we use aren't that different. So you can actually also write out a multiplication rule for Q from this pretty easily. It's just off by some power of 2 based on how many entries you can prime or not. So it's going to be 2 to the length of nu minus length of mu minus length of lambda in terms of number of parts times F nu lambda mu Q nu. But then there's even another sort of nice variant, which is if you take the skew Q Schur functions, then this expands in terms of straight shape ones. Wait, I'm going to take nu over mu here to keep my constants correct. F nu lambda mu. Okay. So this is kind of the analog of, when you have a Schur function, you can expand it in terms of Schur functions with the same coefficients, but here we have to take the dual basis, right?
Skew polynomials are defined by that joint.
Yeah. I mean, I think it's still the Hall inner product, but just restricted to the smaller case of the symmetric functions that are used. Yeah. So the duality that I brought over there is the Hall inner product.
Is this a specialization of what you just mean for the whole little polynomial?
I guess. Well, I don't know if the one I'm going to talk about for like the combinatorial one I'm going to talk about here is, but I mean yeah. I mean if you plug in I guess it would have to be, right? If you multiply how little with polynomials and express it in terms of how little fluids, and then just plug in -1 on both sides, it would restrict to this formula. I'm not sure.
Provided you knew how to multiply all over.
Right. Yeah. I mean, you can do it because they're a basis, but I don't know. I mean, is there a combinatorial formula for the little Richardson rule for that?
Not a nice one, but there could be something. Some rational.
That's actually interesting. I mean, I wonder if this could motivate a general little Richardson rule for how little is or dominant. That would be neat. Some kind of Q-series thing.
Well, that top coefficients then. Yeah, maybe there's not. Well, I mean, McDonald's book would have to
Yeah.
as a rule, but maybe it's all an algorithm.
I mean, it's kind of odd that you're plugging in -1, but then you get positive coefficients.
Right,
So,
I mean,
I'm a little worried.
Also, if you
Yeah, well, like maybe there's a sign reversing evolution, or I don't know. I mean, that's, yeah, I really don't know. It's a good question. Where was I? Okay, yeah, so if we understand these coefficients, we understand how to multiply in the cohomology ring. Oh, and now, by the way, I didn't fill in my quotients, but of course we know now that the cohomology ring of the orthogonal-Grassmannian is just this odd degree power sum thing mod out by the p-Schur function, the ideal generated by the p-Schur functions whose partition doesn't fit in the triangle. So lambda is not contained in the n by n upper triangle. And then, so now I want to talk about some combinatorial rules for this. And here we're going to get into even more funny priming conditions. Oh yeah, and to motivate this, I want to actually return to type A for a second and talk about a different variant of the little Richardson rule. And I feel like this sort of motivates the primed entries a little bit by sort of doubling the picture and looking at the original combinatorics. So, so in type A we had the coefficients C nu lambda mu, and we talked about them as certain Yamanouchi tableau. Of shape mu over lambda and content mu. And so if we take some Yamanouchi tableau like this, which remember means as we read the reading word backwards, we at every step we have at least as many 1s as 2s and 2s as 3s and so on. This is actually equivalent to using Jodo-Tucan or insertion and looking at the rectification of the shape. So T is Yamanouchi if and only if its rectification, which I'll define, is the highest weight tableau, which is basically the unique Yamanouchi one of straight shape. It looks like all 1s in the first row, all 2s in the second row, and so on. So the rectification, which uses a process called Jodo-Tucan, is a process of just choosing. We're going to sort of move this into the corner to make a straight shape. So we're going to choose an inner corner and do a sequence of slides, like a 15 slider puzzle, where you always compare the entry below and to the right of it. And whichever can slide in to keep it semi-standard, you do that one. So let's just do this. This one only has 3 slides. So we're going to slide this one over. Maybe I'll do it on the board. On the board is nice because I can erase. So I can. So if I want to slide one of these boxes into this inner corner, I don't want to slide the 1 over because then I'd have 2 1s in the same column. So I slide this one up. And then now my empty square is here, and I keep doing this until my empty square is outside and I have another skew shape. So now I compare these two 2s, this 2 is going to slide up. And now I'm here, and the only thing I can do is slide the 3 over. If there's nothing to compare with, you just do the only slide. Okay, so that's the next step. And then let's choose another inner corner and do the same thing. So now I'm going to slide the 1 up and the 3 over. And I get this shape. And then finally, I'm going to slide into this inner corner, and the 1 slides up, and the 2's slide over. And oh, look. It's what we wanted. So you can get different rectifications in general, but it's Yamanouchi if and only if it ends up here. So it's known that the rectification is independent of the ordering of the slides you do. And it's actually equivalent to the Schoenstedt insertion that Jeff talked about the other day. So the reason I wanted to talk about this is because another way of generating Yamanouchi tableau is to basically start here and do reverse Jodo-Tucan slides and then see what they look like, right? So if we want to get an intuition for what the shifted Littlewood-Richardson tableau should be, so now this is a fact I'm not going to prove, but I'm going to say that F mu lambda mu is the number of, just to show you the analog, this is the number of tableau T of shape mu over lambda and content. So this is shifted tableau mu, such that rectification, there's an analog of Jodo-Tucan, basically the same thing. So that rectification of T looks like you have a shifted tableau that now has all 1s in the first column, in the first row, all 2s in the second, and all 3s in the third. So this is one Littlewood-Richardson rule, except there's an extra priming condition that's also sort of annoying. So that the first the first I or I prime in reading order is unprimed. Now that seems kind of arbitrary, but it's actually pretty natural. So the way I like to think about this is take the doubled diagram and draw your shifted highest weight tableau. And I have a nice example of something here prepared. So let's take this example. And to even understand what the Jodo-Tucan should be and why we end up with these kind of things with the primes like this, consider the sort of reflection where I just put 1 primes in the column where 1s are in the row, and vice versa, or not vice versa, just 2s and 3s. Okay, so now we have a symmetric tableau, and we can sort of do symmetric outer slides, where first I'm going to do an outer slide in the bottom in some outer corner, and then do the same one in the top, and see what happens, and then cut the shape in half again. Okay, so if I do an outer slide here, I'm going to, let me redraw it. So I'm going to do this outer slide first. Let me keep my staircase. And I'm going to, but I'm going to do it on the whole tableau. I'm not going to like staircase boundary myself. So I'm going to slide the 2' down to keep it semi-standard. Then I'm going to, between the 2' and 3', which one can slide in? The 2' still. And then you actually slide the 1 down, right? Steal from the other half. And then slide the 1' over. We don't stop here. We have to do the symmetric slide now on this square. And to do that, so we're at 1', 1', 1', 2', 1, 2', 2, 2, 1', 1, 1, 1, 3', 3. And if we slide out, we're going to slide this 2 out, and this 2 goes over. And now between the 1 and 1', Oh, so I think I compared things wrong. I'm supposed to compare up and left. Yeah. But anyway, then this 1 slides down to keep it semi-standard, and then the 1' slides over. So what that's saying is an outer slide, if I just ignore everything that happened in the lower left here, an outer slide would be going from this shape to this one above that we ended up with here. So which means we slid the twos, we can think of this as sliding the 2's over, and then sliding the 1 down, and then when I slide this 1 out, it becomes a 1' in order to keep it a semi-standard tableau, right? So strange things happen along that staircase boundary, but they're kind of motivated by doubling the picture and just seeing what happens in the ordinary case.
Recognize this is a cyclic for order 2.
Did you say cyclic sitting?
Yeah.
For group of order 2?
But, I mean, you specialize 2 to be -1, and maybe actually have low points for.
Oh, probably, yeah.
Maybe knows this.
Oh, man.
Better than you know.
That would be really cool. Does anybody know if that's true? You mean just like you plug in Q equals -1 so I guess, I don't know if shifted tableau come up in how little
They
this.
should show whatever objects are counting. I mean, maybe it's not exactly those, but you want to be counting like fixed points for this involution on some involution on the involution tableau.
So for the Hall-Littlewoods, I know combinatorial formulas for the transformed Hall-Littlewoods, the H's, but the P's are a little funnier. I mean, they have like explicit formulas in terms of, you know, ratios of things and products of things, but I don't know. I don't know. That would be interesting too. Lots of good questions. It's an exercise. So, yeah, so anyway, now we can define, that's the sort of motivation for how we're going to define Schubert-Takan on shifted tableau. Oh, maybe I'll leave this up. Shifted JBT. So it's basically the same as ordinary Schubert-Takan with an extra, so same as usual slides, except when you're near the boundary. And there's an exception move, which is if you have 2 eyes at any point in your slide, if you slide this eye down, and slide this eye, then that eye slides over, it's going to become primed. If you're doing an outer slide. And similarly, if you do an inner slide, if we're doing an inward slide and we slide the primed entry into the diagonal, we always unprime it. So this, you can see that if we start from a highest weight and we unprime, based on this extra rule, we're never going to get primes on the diagonal. We're never going to get primed entries starting a strip of i's and i+1. So that's what this extra condition is. That's going to sort of stick with us for all our little Richardson rules. Okay. But then the interesting thing is, okay, so this is a sort of a Schubert-Takan rectification type approach. And there's also a mixed insertion, a variant of Shenstedt insertion that can also give the same result. But there's also a variant of Yamanouchi for shifted tableau. And this was discovered by Stembridge in his paper on projective representations of the symmetric group. And it's a little more complicated than the type A case, but it's still a rule. So the advantage of this is you don't want to have to rectify your tableau and do all those slides in order to figure out whether it's something you count or not. So this is a local rule that says if you have a skew shifted tableau T with the first I or I prime unprimed, you can tell whether it rectifies. So this, rectifies to the highest weight guy, something that looks like that. So we're going to define, so first we're going to define for the reading order, in the reading word of T, we're going to let M sub I of J be the number of i's that occur in the last J letters of the word. So we're sort of looking at suffixes again. But then we also look at prefixes. So we're going to look at P sub I of J, which is actually the number of I primes among the first J letters. Okay. And then it's if and only if for these two things we have the following two properties. So if we're reading the word backwards and we get a tie, so whenever M sub I of J is equal to M sub I plus 1 of J, so the number of i's among the last J entries equals the number of I plus 1s, so usually we would have, in ordinary Yamanouchi tableau, if we had the same number of 1s and 2s, this guy better not be a 2, right? This guy has to be either a 1 or a 3 or a 4 or whatever. So there's conditions on what this can be. But in the shifted case, not only can you not have it be a 2, whenever this is true, we have to have the previous letter, Wn minus J, is not equal to either I plus 1 or I plus 1 prime. Okay? And that's just one condition. Then we also we sort of read the word backwards, and then we have to read from the front and do whenever M sub I of J plus P sub I of J is the same as M sub I plus 1 of J. Oh, sorry. This should be M sub I of N. So the point is we've read the word backwards, we've counted all the 1s and 2s, and now we're going to count 1 primes and 2 primes coming from the left and add them to our totals as we go. So we have our M sub I of the whole thing, M sub I plus 1 over the whole thing, and now we're adding the partial P sub i's and P sub I plus 1 of J. If this is true, then we have W sub J plus 1 also has restrictions. It's not either I or I plus 1 prime, which is just totally bizarre, but it's true. So this is sort of the closest analog to Yamanouchi tableau that you can get. And so F lambda mu nu also equals, if you want, the number of Stambridge tableau, let's call them. Of the right shape and content. So I actually, I'm going to shamelessly end with a plug for my own research, which is I've been, me and Jake Levinson, and who's been in the audience sometimes, and Kevin Prabhu are working on things involving the orthogonal Grassmannian, and we needed a better, a different Littlewood-Richardson rule and different crystal operators actually in the shifted case. So we have a different Littlewood-Richardson rule that doesn't involve reading the word backwards and forwards. Yeah, actually, we could actually just read it forwards and know whether it's valid or not. So I'll tell you our alternate rule. This is a paper coming very soon. I think Jake and I are going to try and finish it next week at this conference. So I think. What's that?
So you won't listen to the talk?
I will. It's between the talks. So. The paper has been delayed because I've been preparing for this.
You have long breaks between talks.
Yeah, exactly. So that's how we'll finish it.
If it was given the archive next slide,
Then you'll know we were paying attention. Yep. All right. So so here's a little preview. So we can define the lattice walk associated to a reading word. So the walk of the reading word of T is defined as, so actually we're going to define the ith walk as you just look at the, so here we also just looked at the i's and I plus 1s. Actually, maybe I should do a quick example of a reading word that has this property. Yeah, so for instance, if you're reading backwards in Stanbridge's rule and you count the number of 1s equal number of 2s, this guy can't be 2 or 2 prime, right? And then that has to be true when you look at 2s and 3s and 3s and 4s and every adjacent pair of letters. So we also have a similar thing where we look at every adjacent pair of letters at a time. And for the ith walk, I'm gonna write the first walk just to show you how it works. And then it's the same for all the other letters. So you take, look at the subword of 1 prime, 1, 2 prime, and 2. And then we're going to make a lattice walk in the first quadrant where we start at the origin and then we read the word. You know, this subword is going to be W1 to WN or something like this. And if at a certain point we're just out here in space and we want to know what direction we're gonna walk on the lattice grid. What direction do we go? We follow this little compass, which says that if it's a 2, we go up. If it's a 1 prime, we go east. We go south if it's a 1, and we go west if it's a 2 prime. But then we also want our walk to stay in the first quadrant. So when it's on the, if we start at the boundary, if at some point in our walk we're on the boundary, we instead have 1 and 1 prime always going to the right, and 2 and 2 prime always going up. Because we don't want to go left or down. Okay. And then, so let's do an example for... Yeah, that's right. We bend the rules when we're on the boundary, but only then. So, yeah, so for instance, let's look at the word 1, 2, 2 prime, 1, 1 prime, 1, 1. And so we start with the 1, and we're reading left to right now. So we start at the origin, and a 1 goes to the right when it's on the boundary, which the origin is. And then a 2 always goes up, no matter whether we're on the boundary or not. 2 prime, now we're off the boundary, so we follow our compass, and we go left. And a 1, we're on the boundary, so where does a 1 go? 1 goes to the right. So we actually get, let me label this down here, we actually get back here to this same point with our 1. So we've done this so far. Now we're at 1 prime. 1 prime always goes to the right. And 1 goes down if we're off the boundary, like that. Here's our 1. And then now if we're on the boundary, 1 goes to the right. Because we don't want to end up down here. So, okay, so there's the walk. And so the theorem is that we have our reading word is Littlewood-Richardson or Stanbridge or whatever you want to call it. So, so I'll just call it Littlewood-Richardson, the Littlewood-Richardson tableau, if and only if each of these walks ends on the x-axis. The ith walk end on the x-axis. Okay, so that's the condition, and so it's a much faster condition. You just read the word left to right, you draw out your walk, you see where you end, and there you are. So.
What's the ith walk?
This is the 1 and 2 walk. The ith walk is for i's and I plus 1s. So you draw all the walks for each of those. We were trying to actually, I mean, we were hoping that we could do like an n-dimensional walk where you just do 1s and 2s and 3s in all different directions. But actually, it doesn't seem like you can glue them together in any easy way. I mean, there might be something that we haven't found yet, but that would be certainly worth investigating. Yeah.
Are any other statistics of these walks coming up, like how far you go on the x-axis?
Absolutely, yeah. So actually we have a whole general theory that's not just these walks that end on the x-axis. If you end up out here, if you have x, y as your endpoint, then that tells you pretty much everything about the rectification of that strip. So if you just take the 1s and 2s and you're asking, what does the rectification look like? Well, there's not actually that many things that a rectification of a word of 1s and 2s can look like. There can't be, because there can't be any primes on the diagonal or in the start. So the only ambiguity, like once you know the shape and the content, the only ambiguity is whether this 2 is primed or not. And actually, up to that priming, this x, y uniquely determines the shape and how it's filled, the content. And you don't even have to look at the rest of the walk moves. Like you don't have to know how many 1s and 2s you had in advance. You know just from the endpoint. And we actually, so as a preview of what our work is going to be, we have crystal raising and lowering operators that change the weight of our word by 1 each time. And the raising and lower operators basically move the endpoint either up and left or down and right. So that's why when it ends on the x-axis, basically that means our raising operators ended and we can't raise it anymore. Except, I mean, I want to have a caveat that we have a very complicated, it's not like a standard crystal. We have this sort of doubled crystal that has 2 types of operators and we need to combine them. But they all do this to the endpoint of the walk. So the walk ended up being super useful in understanding like almost everything about the tableau. And I think it's going to end up being more useful in the future. So I hope. I don't know. Okay. Okay, so in the last 10 minutes, I just wanted to sort of summarize what we've done, and I think I'm going to end with a commercial as well, like Stephen started with. But I'm going to plug in my laptop for this. Okay, so these are the lecture notes that I talked about on the first day that you've all seen. So I just wanted to sort of summarize by going through the lecture notes so that you know what's in the lecture notes too, and hopefully I'll add to the lecture notes things that I said but didn't have in the lecture notes yet. I'll try to do that over the course of the next week. So what have we learned? We looked at this Schubert calculus quiz that we started with, which was just basic problems about intersections of linear subspaces of some n-dimensional space. So we answered 1 through 3 on the first day because you guys are really smart. And then problem 4, we built up the whole theory of the Grassmannian and the Littlewood-Richardson rule and everything to understand why for how many lines intersect 4 general lines in C3. By the way, can you guys see? Is this big enough? Okay. There's 2, and then for problem 5, I let you play with the hook length formula for an exercise, so I've updated this just for this lecture. So it says how many k-dimensional subspaces of C to the n intersect each of k times n minus k subspaces of dimension n minus k non-trivially. So remember, this was the problem of how many. Basically, it translates into how many standard Young tableaux are there of shape k by n minus k, the rectangle. And since I didn't say generic subspace, the answer is C. It depends on the choice of the given subspace, but I've added it's usually B. So B is the answer to our Schubert calculus quiz number 5. C is always the answer, so it's still C. Okay, so then I have the basic outline of all the things we did in the lectures in here. We talked about projective space, affine patches, and how on all conics are the same. Right? We talked about the parabola being an ellipse if we draw it in Salt Lake City. And then just some basic things about projective space. Then we talked about the Grassmannian. So Grassmannian is k-planes in n-dimensional space. This has a structure similar to projective space, and it has a Schubert cell decomposition. We saw how to construct these Schubert cells, and talked about different flags you can define them with respect to. Have the things about the cell complex structure here. And then for intersections, we talked about the duality theorem with opposite and transverse flags. If you remember, that one was we can compute directly. So I wanted to show you, I do have a full proof of the duality theorem in here, because I just sketched it before. And here was our one-line proof, or proof by picture, that there's a unique line between any 2 points in projective space. And then we proved the Pierre rule for the Grassmannian, and that implied that we have this map with symmetric functions. We had the Littlewood-Richardson rule. Here was the 5 tableau that we computed that one day to show a Littlewood-Richardson coefficient was 5. And we connected it with Schur functions, the cohomology, and then we went into the flag variety. So that was yesterday and the day before. We talked about the flag variety and how we can draw out its Schubert cells similarly. We had our Schubert decomposition and cell complex structure on that. I didn't actually talk about Bruhat order, which is worth reading about. There's a Bruhat order in general for any, you have Coxeter groups and you have reflections, and Bruhat order is basically a covering is going up by one reflection. And it just tells you how the closures of the Schubert cells work in terms of the union of Schubert cells. Then we looked at the intersections. We had Schubert polynomials defined with these symmetric difference operators. And we generalized the flag variety by looking at Borel's, which we just talked about today. And then today we got to the orthogonal Grassmannian, so I won't repeat that. Here's all the... Oh, here's this general elimination argument if you want to see the general proof that's not just for that shape, that you cut the picture in half. Okay, and finally, I just wanted to point out I have a bunch of references here. If you guys have other references you think would be useful that you want me to add to the lecture notes, that'd be great. I'm always happy to take suggestions if you find typos in here or whatever. This could be a good resource. So I just wanted to end by saying that, oh wait, this is from before. So I hope you learned something from this mini course, but what I do know is that I learned a ton from teaching this mini course. And it was a great experience. You guys asked so many good questions that made me think about things, that made me learn things, and it was a blast. And I just want to say, like, I find that teaching is the best way of learning things. So this is why, actually, on the first day, I think Francois mentioned my blog. This is why I started my blog. So I have a math blog because I find it hard to learn things, and so I teach them instead by writing them up for an audience that I imagine somebody is reading my blog somewhere. And so Francois obviously read it. No, I was actually amazed. I was in like my second year of grad school, and I wrote a blog post, and Francois Bergeron commented on my blog, and I was like, oh my God, this is amazing. People are reading my blog. So you never know what happens when you blog about things. So no, it was awesome. I mean, I wish people commented on my blog more. So I want to just mention my blog. It's called mathematicalgemstones.com. And the reason I want to tell you guys about it is true. So yeah, I have a page called Contribute, which is tells you how you can contribute to mathematical gemstones. So if you don't want to set up a whole blog of your own, but you want to type things out and understand, maybe you want to understand something better, so you find that a good way of understanding things is to write it, like I do. You can submit it, and basically I'll just look at it, I'll see if it looks appropriate for the blog. My blog posts are generally not too long, they're generally an overview of some, let me go to all posts. Oh yeah, so I have different gemstone hardnesses. So amber is a sort of a soft gemstone, and so amber is for amber posts are for people who just have layman, basic elementary, middle school mathematics background. So I have things about modular arithmetic, for instance. I just wanted to post about it because I had a friend who was from a running group, and he didn't know what modular arithmetic was, so I made this post for him. And then Perl is a next hardness level. It takes some high school level background maybe. Opal is basically for undergrads. Sapphire is for graduate students, roughly. I mean, I try to organize these roughly like that. And then we have Diamond, which is highly specialized posts. I have things about, let's see, I think I have shifted partitions of the orthogonal Grassmannian, right? So there's I mean, I guess this, that one maybe could have been in Sapphire too. And it's not exactly clear, but the point is you can write any difficulty, anything that you think is interesting and fun, or maybe you want to understand better, or you have a good way of understanding. Like often I write a blog post when I'm working on something and I don't understand it, and then all of a sudden I'm like, wait, it's just that. Why didn't anybody explain that to me before? And then I explain it that way so that other people don't have to struggle like I did. So and then I have some miscellaneous posts, but they're just on other things like technology. Maybe I'll post about Sage someday. So then the posts are sort of like, what is the orthogonal Grassmannian? And actually, so a lot of my lecture notes I took from my blog posts, to be honest. But I want to sort of advertise just not my blog, but how useful this is. Because especially as I was writing my lecture notes for this mini course, I found I would go back to the posts I wrote in my second or third year of grad school on Schubert calculus, just the basic Grassmannian stuff, like how it all works, the Schubert cells, and I would look at those posts, and first of all, I would see errors in my posts and be like, how did I think that was true? But then I would also see what were the confusing things back then. What was I confused about as a second or third year grad student? And then I would know how to teach it, because it would be like, well, I know I should say that, because I remember that being like, oh yeah, that's right, that was really confusing, right? So writing these things down as you learn them can be useful for you going back and teaching them later. And finally, I'm just of the opinion that math should have more expository work, I guess, in it. There's a lot of papers that people are already always rushing to publish new material, and I think it's useful to organize it and summarize it sometimes. So if you want to contribute a blog post, please email me and let me know. Okay, so that'll be all.
Thanks, Maria, again for the wonderful presentation you gave. And now we'll break for about 2 hours, and we'll be back